Hello, and welcome to a Spencer presentation on Aero Air Flight Mike Foxtrot 1285 Romeo for aviation safety. A little background information of Flight 1285. The tragic accident happened on December 11th, 1985 in a McDonnell Douglas DC-863. It was carrying 248 U.S. soldiers and 8 crew members from their peacekeeping duties in the Sinai Desert. Their final destination was Fort Campbell, Kentucky, USA. They had layovers in Cologne, Germany, and Gander, Newfoundland. Now here's a diagram of Gander International Airport. But what exactly happened in Gander? They had a successful refueling, then they taxied via Delta, runway 13 to runway 21. Runway 21 is 10,200 feet long and has a downslope gradient of about 0.34%, which should have aided them in their takeoff roll. About 51 seconds after brake release, the pilot rotated at 167 knots. They did achieve liftoff, however they gained very little altitude and crossed the transatlantic highway dangerously low. Then they struck terrain about 3,000 feet past the departure end of the runway. So here's a more terrestrial view of Gander International Airport from Google Earth. You can see runway 21, the longest runway, and the transatlantic highway crossing just to the south. So why did this happen? The investigation was done by the Canadian Aviation Safety Board, or the CASB. According to the CASB, ice contamination on the leading edge and upper surface of the wings was the leading cause of the accident. This is well explained by the time of year and the geographical location of Gander. There's plenty of water for moisture, and the cold temperatures are due to the location and the time of year. Also, human error plays a significant role in most aviation accidents. So how does ice contamination affect a plane's ability to fly? When the wing of an aircraft experiences an accumulation of supercooled water droplets, it changes the surface of the wing, or the wing camber. This dramatically increases the drag and the weight of the aircraft, which in turn reduces lift, making an aircraft moving at the rotating minimum stall at the end of the runway. And as you can see here, an accumulation of ice on both the wings and the body of the aircraft increases the weight and increases the drag. Therefore, you need more lift and more thrust just to keep the plane in the air. Preventative measures. A thorough pre-flight inspection is the first and primary protection against icing hazards. Not only are we looking for structural hazards that can cause in-flight failure, but also an accumulation of frost or ice. Keeping your plane in a heated hangar protects it from precipitation and will melt any ice that may have formed. De-icing fluid and other equipment such as pneumatic boots, weeping wings, bleed air heated surfaces, or electronically heated surfaces also help remove any accumulation of condensation particles. If all else fails, the pilot in command has the right to deem the conditions unsafe and delay the flight. Improving safety. This graph represents data from 1942 to 2016. It shows how the implementation of better safety measures and updated rules and regulations have helped to reduce the number of commercial aviation deaths. This data excludes terrorism, shoot-downs, corporate jets, and military accidents. Reason's Swiss cheese model. This is a model of accident causation proposed by James Reason. It stated that most accidents can be traced to one or more levels of failure: organizational influences, unsafe supervision, preconditions for unsafe acts, and the unsafe acts themselves. The slices of cheese represent an organization's defenses against failure as a series of barriers. The holes in the cheese represent individual weaknesses in parts of the defense system. When all of the holes in the cheese align correctly, this permits a trajectory of accident opportunity, which may lead to an accident. Now let's apply the Swiss cheese model to Flight 1285 by breaking down our 4 slices of cheese. 1. Organizational influences. The pilots may have not had the proper knowledge on the hazards of icing conditions. Also, poor flight planning with respect to the weather forecast contributed. 2. Unsafe supervision. It was noted during the investigation that the plane was not de-iced prior to takeoff. The flight engineer performed a pre-flight inspection and deemed it safe. 3. Preconditions for unsafe acts. Precipitation conditions were favorable for the formation of ice during the approach to Gander. During refueling, there was a continued exposure to freezing precipitation. 4. Unsafe act. The flight was still cleared for takeoff, even though there was a high safety risk. Now, looking back at our preventative measures, the safety risk could have been lowered significantly with a more thorough pre-flight inspection, implementation of de-icing equipment, or just simply leaving the plane in a heated hangar. A personal interview was conducted with aviation professional and aeronautics professor Deborah Henneberry. What do you think are some major risks in aviation today? She said fatigue continues to be a leading threat to aviation safety. A newer concern has been the deterioration of hand flying skills due to the amount of time the airplane is flown via automation. In the past, pilot error was the leading cause of accidents. What do you believe to be leading causes today? She said the most common answer is that these are due to technical failures. However, machines do not fail by themselves. If part of an aircraft breaks, it is either because it has been designed insufficiently for its intended purpose, it has been built or maintained incorrectly, or it has been used in the wrong way. When you probe into technical accidents, human error will usually be involved somewhere. With automation and advancing technology, how do you believe these systems can mitigate error without a reliance on these systems? She responded with automation, when used correctly, can increase situational awareness and mitigate pilot workload. In more advanced airplanes, systems can prevent pilots from inadvertently flying the plane in a way that could cause structural damage. Automation does not replace good judgment, however. Pilots must continue to maintain proficiency and guard against complacency so that they do not become overly reliant on automation. They must also stay vigilant when using automation so that they do not experience automation's surprise. So how does ice contamination affect an aircraft's ability to fly? Ice adversely affects how air moves over the airfoils. Lift is greatly reduced. Ice, especially clear ice, also significantly adds to the weight of the plane, thus increasing the amount of lift needed to maintain flight. How does de-icing equipment used today help reduce ice-related accidents? Modern de-icing fluid contains glycol, which has a low freezing point. The Type 1 de-icing fluid is used initially to remove ice and snow that has already accumulated on a plane. It does not create any long-term protection though. Type 2, 3, and 4 fluids are thicker and are used to prevent ice from reforming. As a result of the thicker fluid, icing protection lasts longer. So this concludes my presentation. I hope you guys enjoyed the video. Hopefully you can use this information to help reduce future accidents due to icing. Fly safe.